Exercise 237 gives you nicotine. It says nicotine is a toxic substance present in tobacco leaves. There are two lone pairs in the structure of nicotine, so that there's going to be one on each of these nitrogens. Because each of the nitrogens already has 6 electrons drawn around it, so it just needs those extra 2 to get the full 8. So it says, in general, localized lone pairs are much more reactive than delocalized lone pairs, because the delocalized lone pairs spreads charge out over a larger area, and so in any individual area there's a smaller charge, and so the molecule is more stable. With this information in mind, do you expect both lone pairs in nicotine to be reactive? And justify your answer. So if the lone pairs are localized, then we would think they're reactive, and if they're delocalized, then we'll think they're unreactive. So localized, reactive. And if they're delocalized, then unreactive. Okay, well, let's just go through it one at a time. We've got this lone pair over here, and that lone pair is not involved in any resonance patterns. It's not allylic, because if you go one atom over, you're not at an atom in a double bond, and it's not next to a positive charge. There are no positive charges right next to it. So it's not involved in any resonance patterns, and therefore it is localized. It's localized, and because it is localized, the charge on those electrons is stuck just in one atomic location. In general, when you force charge to be in a small space, it pushes against each other and becomes reactive, as opposed to when you spread charge out, it becomes less reactive. So it's localized, and so that lone pair will be more reactive. Okay, then the other lone pairs. Now, these lone pairs here on the other nitrogen are a case that we've seen before in a previous problem. We saw something a little like this in D before, in the previous problem in 236. So what happens here is the nitrogen has to have p orbitals on it in order to have this pi bond. Now those p orbitals, in order to form the pi bond, have to be parallel. That's the only way where you'll get that overlap that is the pi bond. They have to be parallel. If one of them is not parallel with the other, then you wouldn't get that special pi bond. So in order to have the pi bond, you have those two parallel py orbitals, and that's true all the way around here, right? You have a bunch of py orbitals there. And it's because of that that the electrons are able to fly around the whole thing. After all, if you have parallel p orbitals on multiple atoms, if that's a pi bond, why isn't this a pi bond? Like, where does the pi bond start and stop? It doesn't. The electrons just fly around the whole thing with all those parallel p orbitals on adjacent atoms. Okay, so that's what the double bond is already. This double bond exists because the nitrogen already has a py orbital that's stabilized in this way. So then, what type of orbital would the lone pair be in? Well, if it tries to be in a p orbital, it has two choices. It could be in a px orbital, so something like that. Actually, let me just erase this so I can draw it on top. Something like a px orbital, but notice that wouldn't line up and create a pi bond with any of the p orbitals. Definitely not the ones that this is allylic to, right? And because the orbital would not line up with these other p orbitals, it's not able to, the electrons are not able to spread out and be involved in resonance like you would expect. After all, these lone pairs are allylic. If you go one atom over, you're at an atom in a double bond. And usually, almost always, that will give you resonance. The one time that it doesn't is when the lone pair is on an atom that's already involved in, in a double bond. Because the py orbital that you would need in order to be parallel to those is already taken. It's already taken by that pi bond, and so the lone pairs can't exist in it. So if it's in the px orbital or if it's in the pz orbital, it still wouldn't be parallel to those, and so it wouldn't be able to form those pi bonds. So there's no reason why this lone pair would prefer to be in a p orbital. The nitrogen would just mix the two remaining p orbitals with the s orbital and it would be sp2 hybridized. But the point is that this lone pair is not able to delocalize itself. It is also localized. And so it is also reactive. Because the negative charge is just stuck on that nitrogen atom. And it's the charges in those lone pairs sticking to molecules in your body that partly makes this such a strong molecule, or makes this molecule respond so strongly in biological systems.